Year 13, first lesson. Well, first lesson if you're going to finish your remaining parts of what is your cancelled A-level in the sense of what the government are doing. So if you want to do that and you want to make sure you've covered all of the course, because chemistry may be important, and I've discussed this with a couple of you, then acids and alkalis is the main remaining thing. As you can see, got titled there, calculating pH. Up till now, pH has just been that number with some colours. Year 7 use it, so on. But actually it's a calculation. It's not just a random number put with some colours and a universal indicator. It actually is a proper numerical value. So just a reminder, first of all, acids are all about hydrogen ions, H plus ions, and alkalis are all about hydroxide ions, OH minus ions. So calculating pH is to do with the concentration of those two ions. Actually, it's only to do with the concentration of hydrogen ions, but you will come to that. So, first of all, really, I've got a script there, by the way. First of all, we need to know exactly what pH is. So, firstly, the term pH means something. The H is the hydrogen ion, but that means a particular mathematical thing. It's a button on your calculator. It means minus the value that is determined by the log button on your calculator. Now for different calculators it works in a different way. Some of them you put the number in, press the log button. Others you press the log button, put the number in. Depends on your calculator's chipset. So minus log, technically it's minus log to base 10, but the button on the calculator called log always does it in base 10. There is a button that does it in other ones. Way too much for a chemist, that. So pH, firstly that. So therefore the definition is minus log of the hydrogen ion concentration. So if you know the hydrogen ion concentration, it goes in the calculator, press the button, it will come up most of the time as a negative number. You just take the negative sign off. Occasionally it comes up as a positive number and that gives you a negative pH. Oh yes, contrary to the colour wheel that is on the wall of my lab, or all the values that you've seen before where pH goes from 1 to 14. Firstly it has decimals if you do calculations, and secondly it can go past the 1 and go to 0 or even negative when the hydrogen ion concentration is high enough. So, little example, I think is probably the way forward. Now, if we had, just going to rub a little thing out, my yellow cloth. There we go. So, we want to do the concentration of straightforward strong acid. Now this is what you do with strong acids. Now there aren't that many strong acids that you do this with. HCl, HNO3, sulfuric acid. Sulfuric acid is a bit of a complicated one. We'll come back to sulfuric acid another time. So taking HCl, there is an assumption that you make. So normally you would do that when you're talking about acids, but for strong acids it isn't an equilibrium arrow. It is full on complete reaction, and that means that it goes, in this case it forms those. If it was nitric it would be H plus and NO3 minus, but it does 100% this and none of that. And that's really important when it comes to doing this calculation. So if we were doing an example of this, and what we were looking at is 0.066 I think I wrote down. Yeah, 0.066 concentration. What's the pH of that? Now, there are two things you can do. You can get that solution made up, put a pH probe in it and see what it says, or we can just calculate it, which is what this is for, because quite frankly, in an exam, that's what you'll be doing, if you ever take one. So, you take that. Now, this 100% thing means that that concentration there gets turned into that. The concentration of HCl means that that and that are firstly equal, secondly that is the same as that. So the concentration of H plus, because of this 100%, that's a terrible zero, 0.066 is that concentration. Moles per cubic decimeter, of course. So literally that, in a calculator, press the log button, so you then get a pH, and it comes out, as I've done it beforehand, comes out with a pH of 1.18. That means the calculator said minus 1.18, so we write down the negative of that value, which is plus 1.18. And that's it. For strong acids, the stated concentration is the hydrogen ion concentration goes in a calculator and gives you the pH. Now, that's the easiest thing. Alkalis, slightly more to them. Now we've got some questions that you can do shortly, but we'll go through the strong acid, strong alkali, and then we'll tell you what to do. So if I change that to strong alkali, what you now would have is something that we would classically think of as a strong alkali. Sodium hydroxide, potassium hydroxide is another one. Obviously those are untrue. It then becomes Na plus and OH minus. 100% again, because strong means 100%. None of that as a pair. Everything in solution, because remember this is all in solution, I've left the state symbol out. So everything would be 0.066, 0.066, assuming I'm talking about the same concentration, which I'm going to do. So we're going to find out the pH if we had sodium hydroxide at that concentration. Now that's not true, because you need a little extra step. And that's where the first thing that you need to remember that's not obvious from what we're doing here, I suppose, and that is a thing called Kw. Kw is an equilibrium constant. Kw is an equilibrium constant that represents itself in this calculation. Hydrogen ion, oh dear, not good. Hydrogen ion concentration and hydroxide ion multiplied together give you a value called Kw. It has the units of two concentration units, but it's temperature dependent as well. So 298 Kelvin, standard sort of temperature that we always talk about, 298 Kelvin, it has a value of 1.00 times 10 to the, interesting little number coming up here, minus 14, because that's the highest pH you can have. And that's why, because of Kw. Now it's temperature dependent, so if you increase the temperature, Kw gets bigger. We're not going to get involved in doing these calculations at different temperatures, but Kw does have a slow, it's not a massive increase, it slowly creeps up. And like I said, it has double concentration units, so it's mole squared dm to the minus 6. Now, if we're doing this pH, that is the concentration of hydroxide ions. That, we don't know. But we do know Kw. So 1.00. concentrations of hydrogen ions. And if you do that, and you put that in a calculator, maybe you're doing the calculation with me with the calculator? Oh, you're not? Okay. Well, the answer is 1.52 times 10 to the minus 13, and that's concentration, so it's moles per cubic decimetre. I've run out of board. And what you then do in a calculator, get the log value, and the log value is 12.82, which is the sort of number you would expect for an alkaline solution, relatively strong alkaline solution, quite a high pH number. 7, that's that neutral pH number. 7.00 is in reality what that is. So we've reached that point where you've got enough knowledge to give yourself a little practice. There was on the Show My Homework 2 attached documents. One has got the questions, one's got the answers. You're not ready for all of them yet. There's other bits of video to take you through what you need to do. But you are ready to answer question 1, parts A and B. Don't look at part C, that comes up after doing some stuff to do with weak acids, because weak acids, the assumption of 100% not true. We will then come back after that and do weak acids. See you soon. Welcome back. So, that's a weak acid. So we're here for weak acids in the second part. Weak acids, definitely in equilibrium. This concentration much lower than it would be for a strong acid, probably 1% of the value it would be for an equivalent concentration of strong acid. So that means that this equilibrium is really important. This equilibrium, standard equilibrium setup, like a Kc, but it's not called a Kc, it is a Kc, but we call it a Ka because it's so common it gets its own equilibrium constant. The acidity constant, Ka, you look at that, it's going to be those two divided by that, the concentration on the left. Now, when you do that, it allows you to find the H plus concentration. Now, there are 2 schools of thought with that. The first school of thought is do it properly. If you do it properly, oh, you get quadratics with all sorts of horrible numbers in. So what we do, for simplicity's sake, is we have another assumption. So we had an assumption with strong acids, there's an assumption with weak acids. Now the assumption here is that the level of ionisation, which is what coming this way is called, the level of ionisation is so small, when you get a concentration of those, but the concentration of those is so small that the concentration of the actual acid itself that is sitting in solution without being ionised has barely changed at all. It has, but you assume, for mathematical simplicity and a couple of decimal points difference, that it hasn't. So if we had a concentration of, well, let's not use the same value as last time. So we had a concentration of 0.0425 moles per cubic decimetre of the ethanoic acid, which is what this is. Now, you can't do this without having a value for Ka. Ka also has units. If you look at 2 on the top, 1 on the bottom. Now, this one, the Ka value, so there's the units for Ka, and it has a value of 1.75 times 10 to the minus 5. Now, when you do that, and we've got that value will be this value because we said the assumption is that it changes so little it's not worth considering. We have no idea what that is. But what you do is you have this numerical, those two can't make hydrogen ions without making ethanoate ions in exactly the same amount or same concentration. We don't know what it is, so we're going to call it X. But it's going to be X squared because hydrogen ion concentration of that are the same. X each, X times X is X squared. And then we said that the assumption is that this 0.0425 hasn't changed to any significant extent. So then, concentration of hydrogen ions involves a little rearranging of that. So the Ka value times the concentration, and we have to square root it. And when you do that, you get a hydrogen ion concentration of, oh, goodness, oh, I can't read that from over there. I've got to look at my bit of paper for the number because it's quite complicated. 0.000. Look again. 8624. There we go. All right. So the concentration of hydrogen ions is that. So you then minus log to base 10 as it is, or minus log. Do that. The pH then, because that's the hydrogen ion concentration. The pH, small p, capital H, 3.06. There we go. So you get a Ka value which is not the same for every weak acid. As weak acids go, that's got to be in the middle of strength wise. Some of them are a bit bigger. Some of them go right there, minus 10 to the minus 10. They're very weak acids. And yeah, you have to go through this process. You can also do the process in reverse when you know the hydrogen ion concentration because you've been told the pH. So you then do, if you want to know the hydrogen ion concentration, you would go 10 to the minus 3.06. That's a 3, it looks like a 3. And that allows you to get the hydrogen ion concentration there. And then, not any better. And then you can then work your way back through because the hydrogen ion concentration is the same as that. And then you've been, well, you might be working that out, you might be working that out. There we go. So that allows you to do weak acids, which is the remaining part of question 1. But I also want to do one little extra thing, which is what happens if you've got what's called a dibasic or a diprotic acid. Now we're going to take a little pause. So here we are with sulfuric acid. Sulfuric acid is dibasic or diprotic acid, but the first ionisation, we think of it as a strong acid. The strong acid bit is really about the first ionisation. The strong acid part, 100% split up into hydrogen ions and hydrogen sulfate ions. Now we think of it as having quite a lot of hydrogen ions, but actually most of them are sourced from here. Now when you do that, this 100% means whatever concentration of the sulfuric acid is the first H plus concentration, and then you use this, which is the same as that. This, the value of hydrogen sulfate, feeds into the second one, where it becomes a sulfate or sulfate 6 ion, and a second lot of hydrogens that you add on in the calculation. This one is, as weak acids go, quite strong, but it has a Ka value, so we can combine strong acid and weak acid in the same calculation in this. So I've got a question here. What is the pH of 0.05 moles per cubic decimeter sulfuric acid? So first thing is, off that first top ionisation, concentration of hydrogen ions is 0.0500. And then we have to determine what's the add-on for doing the second one. So this is the first H plus concentration, but it's also the hydrogen sulfate ion that feeds into the second one. So the concentration of hydrogen sulfate is the same as that there because of the way that equations work. Obviously you can't make one without the other. And then we got a Ka value for this second one. So 0.0100 is the Ka value, and it equals, same idea as before, don't know the H plus or the sulfate concentration, so it's x squared, and then this value, or this concentration, is coming out of the first equation, so it's 0.0500. So when you do that, concentration of hydrogen ions for the second second is the square root of times 0.05, leaving out all the trailing zeros. And you do that, it's 0.0, just checking, 224. There we are. I didn't think you'd want to see me using a calculator, so I pre-prepared all the numbers, and then I can't read them. Always the way. So, you then have got that hydrogen ion concentration and that hydrogen ion concentration joined together. So when you add them together, you get 0.0724, and when you put that through the standard pH calculation minus log to base 10, you get a pH of 1.14. Majority of that is from the hydrogen ion concentration of the first one, 0.05, but they're still reasonably significant. So therefore, you combine the two in that calculation and get a true representation of the pH. However, there is something that you need to be aware of when you get stronger solutions. 0.1 is about as good as these calculations work properly. Now, it might not be necessary to know this, but there's a thing called activity, where if the concentration is over 0.1, you don't quite get all the ionisation taking place because the ions get squashed together. We're not going to go into the activity values. We just do the straightforward calculation. But so this would be fairly much the concentration because these are below 0.1. Which means you're now ready for finishing the rest of question 1, doing question 2. Don't do question 3. Question 3 is for the follow-up video that I haven't yet filmed, and well, that'll be about mixing strong acids and strong alkalis together and getting a resulting pH. So right now, you're ready to go and do your own work. The answers are up on the Show My Homework, and I look forward to seeing you again for more adventures in chemistry, because quite frankly, everything's an adventure right now. And I'll see you soon. Bye!